Okay. So am I audible?
Yes, sir.
Okay. Okay. So then let's start. Okay. So uh, in the last class, we were discussing about the electrons' properties in a band. So the left hand side, this picture. So whenever I am showing you images, so this is from the book, this Ashoka Sap, and that's why I'm also like copying the figure number as well, so that when you go and read the book, so you know which sections you need to read. So this left-hand side picture, this figure A, shows basically the schematic representation of the energy band. So in a metal, so what we have is electrons which fill up from the bottom of the band up to a level which is known as the Fermi level. So Fermi level is Fermi level indicates the energy or the energy of the electron in the highest occupied state. And this Fermi energy can be different for different materials. And then in the same band, you have some empty states that are available where electrons they can go to those empty states if there is some external uh, a field is applied, or if you give some energy to the electron, so they can go to those empty states. Otherwise, so this picture what we are showing here is corresponding to a temperature T equal to 0 Kelvin. So here one interesting thing which we can actually so we will look at it later on, but I want to mention here again. So when you see this electrons occupation, how they are occupying the energy levels, so there is a distribution is inherently is there, which is known as the Fermi-Dirac distribution. So we will look at it later. But one thing which I can mention here, so the electron probability distribution at T equal to 0K. So what this probability distribution says that the probability of finding an electron at any energy E, so would be equal to 1 when your energy is less than EFO, and it is 0 when E is greater than EFO. So this is what, from the simple schematic picture, one can say the electron distribution, the probability distribution is very different from a classical distribution that you normally, like Boltzmann distribution that you have come across. So it is a different distribution of particle. Uh, and this is due to these are quantum mechanical particles. Okay, so these are they follow Pauli's exclusion principle, and that's why they follow this kind of statistics. So where the probability, or so it can be F or P, whatever you want to say that. So the probability of finding an electron in an energy state E will be 1 when energy is less than the Fermi energy, and it will be 0 when energy is greater than Fermi energy. So this is at T equal to 0 Kelvin. Now this the second figure actually represents the energy of this particle as a function of momentum. So in the last class we also saw that like each electron, uh, when the electron in these bands, so which, let's say we are saying it is a conduction band, or a partially filled conduction band, because it is not fully filled, so it is a partially field conduction band. So this C dot B means it is a conduction band. They are the energy is almost, it is similar to a kinetic energy. So the energy you can write just simply by p square by 2a. So that means energy of the electron can also be expressed in terms of its momentum. Now this is useful when we talk about the uh, drift of electrons. From that sense, it is useful, like in order to understand the conductivity of materials, it is useful if we represent it in terms of the momentum instead of energy. Uh, Now, when you put that in a band, so this is a picture of a one-dimensional band. So from the relation between E and P, it will be a parabolic function. And clearly, when we say two particles, let's say on the, so the black dots here, or the closed spheres or circles represent occupied electron state. So here, this is occupied, and this is, here you have empty states, so where there are no electrons, and this energy is the highest energy that is occupied is the Fermi energy. And when you look at the momentum, so some electrons have, or you have half of the electrons which have a positive momentum and half have a negative momentum, and that is why the average momentum is equal to 0. Okay, so this is so some will have, so this is a one-dimensional thing which we are showing. So if we have n electrons, so then n by 2 will have a positive Px, and n by 2 will have negative Px. However, when you take the total momentum of the electron in the band, so this comes out to be 0. And that's why there is, so the P total, that is equal to Px plus P minus x, which will be equal to 0. So this is the behavior of electrons. So we are not studying the behavior of electron individually, but electrons as a collective form, or what we call as a gas, electron gas. So we are treating electron as, or the electron, this n electrons, which are in the conduction band. So we are treating them as a electron gas. Sometimes it's also known as a Fermi gas as well, because of this name. So they are sometimes used as well, Fermi gas, this electron collection of electrons in the conduction band. So they are also called as Fermi gas as well. So that means when you have no electric field, so the situation looks like this here. Okay, so you have some electron, or exactly half of the electrons with positive momentum and other half with negative momentum, and therefore the net momentum is 0. Now what happens when you are applying electric field E? So in that case, so some electrons will get accelerated and some electrons will be decelerated, and that means so some electron will gain energy and some electron will lose their energy. So this we represented something like, so we can say the initial the velocity will be different. So the momentum will change because of this external field E, because due to the external field, so you have a acceleration. So let me say, you have an external field E. So this is, since it is in one dimension, so we are saying it is Ex. and that leads to a change in the energy as well as momentum of the electrons. Now, basically this electron or the electric field will impart a force on the electron, which will then get accelerated uh, by m, and then there will be a change in the there will be a change in momentum and energy due to the external field. Okay, so how it will change? So basically your when we say the momentum px, the positive one, let's say it is in the beginning or unperturbed state when there is no electric field, so px0, yes, let's see the question. There is some question. When electric field is 0 at room temperature, then electron may have energy greater than Fermi energy, so average momentum being 0. When electric field is 0, then electron may have energy greater than Fermi energy. Yes, electron will have, so some electron can go to the unoccupied level. Yes, yes. In that case, still you will have, so the possibility that the probability that electron, so there is equal probability of electron with positive momentum and negative electron both going to the energy level, because going from one energy level to the higher unoccupied state, it doesn't depend on what is the momentum of that electron. So when they gain energy, yes, that is when you are not when t is less than equal to 0. So the question is, so if we are at room temperature, so let's say we are at room temperature and you are applying an electric field is 0. So in that case, electrons can go to the above Fermi level. Okay, so this picture what we are representing here is only at t equal to 0 Kelvin. But when t is greater than 0, so let me draw it in another. So let's say when t is greater than 0 Kelvin, so you can have, so some of these state can be occupied. That means some electrons from here, they can jump to the higher occupied states or unoccupied state because of the thermal energy. So they get the thermal energy, and it is possible that electrons which are close to the Fermi level, so they will go to the unoccupied state in the above the Fermi level. So this definition of Fermi level is true, holds only when T is equal to 0 Kelvin. Yes, yes. So even if you are not applying any electric field, if you are just increasing the temperature, so then also you can have electrons can go or occupy states above the Fermi level. So that is possible. So we will see that in the when we talk about this Fermi-Dirac statistics or the distribution, you will understand it better. So now. So when we talk about, so this is a picture for what we have is for metals. Okay, so this is what we are talking about now, metals. Now when you are applying, when you are increasing the temperature, for example, you are at room temperature, so electrons will occupy these energy levels, but the probability of, but there will be no change in momentum, right? Because electrons with momentum p, a positive momentum, and electron with a negative momentum, they are equally probable to go to this go and occupy this unoccupied state. Okay. Okay, so now if you have a increase or apply external field, so this picture what we are showing is a one-dimensional system, which actually the concept holds true for three dimension as well. Although the mathematics and everything is different, and you need a advanced knowledge of quantum mechanics, but the concept and fundamentals are very same. So what you have is Px will change. So you have Px plus it will be E tau. So there will be a factor of m as well, and P minus x will be P x0, which is minus x0 plus E. So here Ex, this is Ex star plus m. So m is, let's say, the mass of the electron. So you definitely the momentum will change. So correspondingly, the energy will also change, and due to this change, so the net, let's say now write down the total of the P total. This is again in one dimension, so I am not writing the vector form here. So total momentum will be this delta P will be greater than 0. And this change in momentum will be in the positive direction. So here, this is shown here in the picture. So now the change, this average momentum change, the average will be greater than 0. So that means there is the electron gas has a momentum along the positive x-axis, or that means a current in the positive x direction. So due to this electric field, the electron will move in the negative, positive x direction, because electric field is, they are moving opposite to the electric field, which is applied along minus x, and you will have a current in the minus x direction. Now this delta E, this change in the energy of electron is only happening. So few things you need to notice, or which is quite distinct here. So only electrons which are close to the Fermi level, so they are going and occupying the states which are available above the Fermi level. Okay, so the shift is in such a way that this change in delta E only occurs close to the for electrons which are close to the Fermi level. Now this process has to stop, because electron will get scattered at some point. They have to get scattered due to the lattice vibration or any impurities or anything. So electrons have to get scattered, and that's why you get the resistance. Okay. Now, what it means in terms of this, when we describe it in terms of this electron, this band structure, what do we mean by this scattering here? So scattering means, or let's say we say scattering or collision. So so we have so net momentum, and that leads.
Said in the expression Px equals to Px naught plus Ex tau into Ne, I don't think that we should uh, multiply by Ne here, because Ex tau is already matching with the dimensions of momentum.
This is Ex, so this is
Force
oh yeah, so
into,
you have
yeah.
a m already there, yes. So this is acceleration into time, so it is already the factor m is already there, right? Correct. Okay. Since so this leads to a current in negative x direction. Okay, so the electric field is applied in the negative x direction. So electrons will flow along the positive. The shift is positive x, and the current is in the negative x direction. Now, how do we account for any collision? So that's because electrons, so this drift, this shift in momentum has to stop at some point, because the electron uh, will get scattered. So there will be some scattering or collision, and that is leads to a positive some resistance to the flow of current. So now when you look at this scattering or the collision, so what happens basically, uh, now again we go back to this picture here. So we have electrons which are occupied up to a dash here, let's say. Okay, so this is representation only. So we say they are occupying up to a state A dash. Now this electron at A dash, so this electron, so will get scattered and jump to an unoccupied state. Okay. Now, if it jumps to unoccupied state, so definitely there are states which are available, and which states are available? Those which are above this B dash. So the electron from A dash, or the which is occupying a state at A dash, so it will scatter. After scattering, so it will jump and come to an empty state, so which is this empty state here. So this is the unoccupied state. So this electron will jump from here to here, this unoccupied state, because that is the lowest energy that is available for it. That means, and in order to do that, so there will be a change in momentum immediately. So the electron, which has a positive momentum, it has to change its momentum, and then only it can come from this point to this point. Okay, so and the change in momentum is like it has a positive momentum, and due to scattering, so it goes from a positive momentum to a negative momentum. So this is what a scattering process would look like. Okay, so there will be a change in momentum. So we will say, so this implies there will be a change in momentum of electron. Basically we say it jumps from, so if you follow the picture, jumps from A prime to unoccupied state above B prime, and definitely the change in energy will be very small. So there will be a very small change in energy. And now if you say, like in the scattering process, so it changes, so there is a change in momentum. So where this momentum will come from, or where this momentum, extra momentum, so there is a change in momentum delta P due to a transition from, so electron, the momentum at A prime to when it goes to a minus P, something like a B prime. Okay, so there is the net change in momentum. So where this momentum will come from? It comes from the crystal itself. Okay, so this change in momentum will either be given by the crystal or the lattice. Either it will be given by the lattice or taken by the lattice. Okay, so this extra momentum will either, so there will be a transfer of momentum between your, so it's a electron momentum will be transferred to the lattice or crystal. So remember this crystal, why it can do that? Because crystals are really heavy and they have really large momentum, or the lattice, because these are heavy ions. So their momentum is quite high because they are massive, mass is high. So therefore they can actually take this change in momentum, so they can absorb that momentum, uh, or they can also give the momentum to electrons sometimes as well. Okay. So this is how we can account for the collision or the scattering process. And then once we have this jump to this unoccupied state, so again the same process. So some electrons again will move to this A dash or A prime, and then electron from there will get scattered, and this process will continue. And you will have a continuous flow of current. So to understand this conduction in terms of the band structure or the picture here, so 3 points which are important to note down. So one is, let's say, so electron at A prime flips its momentum. So which is this A prime is close to the Fermi energy. Then when a steady state is there, that means there is a continuous flow of current. So under steady state condition, that means we have a continuous flow of current. So the lattice scattering replenishes the electron from A prime to states above B prime. And another thing which I missed to mention here, so one important thing. So when you look at here, so all the electrons, okay, all the electrons below B prime on the negative x-axis, on the negative momentum axis. So all the electrons here, so they have a counterpart in the they have a counterpart electron with a positive momentum as well. So therefore, all the electrons which are occupied below B prime basically, so on the negative side, so they have electron which have also positive momentum, and therefore the total momentum due to those electrons is actually zero. And if you look, so that means they actually do not really contribute to the conductivity. Okay, so the conductivity is only happening due to electrons which are present close to the Fermi level. So the electrons which are basically way below the Fermi level, far away from the Fermi level, so those electrons normally do not contribute anything to the conductivity process. So this is the third and most important thing to remember here as well. So electrons below B prime have, or let's say below B prime with a negative momenta have equal number of electrons with positive momentum, and that means the um, that means electrons only close to the Fermi level contribute to conductivity process. Okay, so only electrons which are near the Fermi level, so they are only, as you can see, are participating in the conductivity. So electrons which are below B prime, so they do not contribute at all because the net momentum change due to them is actually zero. So this is one important thing which comes out from the this band structure. Okay. So this picture of this how this conductivity happens if you look at the electronic band structure, so can even further be simplified using this picture here. And normally this is the picture what is used in most of the when we talk about conductivity and materials, considering looking at their bands. Okay, so here we have a picture. Uh, so we have a material and we are applying a voltage across it. So that means there is a electric field. So what is the electric field here? So this is a schematic that we want to represent the whole thing what we explained. So can be shown here in a easy schematic way. So we have a electric field Ex, which is given by minus dV by dx. So V is the voltage we have applied, and uh, due to this applied voltage, so electrons will experience a potential, okay, which is given by what is the energy. The potential energy is equal to EV, whatever the value of the voltage at any point x, so they will have that potential, or it will be, if it is electron, so it will say minus EVx. Okay, so that is the energy, extra energy that the electron will have at any point x, depending on where x is. So you can say the potential, the electrons which are really on the connected to the negative potential. So normally we say this is at zero potential. So here V will be equal to 0, and here this V will be equal to your applied voltage. So that's why you have a voltage gradient dV by dx, and that is basically your electric field. So this is what here in the graph is shown here. So we are plotting in the x-axis the potential, and potential is 0, or the energy of electron will be 0 here on this side, and it will be maximum on the other side. And what is that in terms of when you look at the band structure? So initially what you have is, so let me draw the picture here so that things will be clear here. So initial picture was, we have, this is the occupied state, this is EFO, okay, so this is your bottom one, and so on. Now when you are applying an electric field E, so what happens? So you are providing extra energy, potential energy to these electrons, and in terms of the band, there will be a bending of the band. Okay, so what you see here in this picture is the bands, they will bend, so that depending on how much potential or the voltage you have applied. So since on the left side the potential energy is 0, so the band will, the level, Fermi level will remain where it is like before. However, when you go across the solid along, let's say this is x-axis, so we are going across the solid. So since there will be a addition of a potential minus EV, so everywhere, so we will have a change E minus EV. Okay. So depending on the value of V, this voltage, so energy will change. So on the left side, V is 0, and here you have V is equal to minus EV, and that is reflected in terms of what causes is, it causes a bending of the band. So all the levels will bend, uh, and this is known as a band bending. Band bending occurs due to electric field Ex. So due to this applied electric field Ex or voltage V, so the bands, they will bend, they will bend in such a way that you have a, so it's like you have a slope, and then it is easy to explain the flow of electrons now. Okay, so we say electrons will flow from this to this side. Okay, and since there is a slope here, so that means electrons will move from the negative or x equal to 0 to positive x, and you have basically a flow of current. So this is a easier way to represent whatever we explained like in the previous picture, where we have this parabolic picture. So this normally can be represented in a simpler way by showing that due to the application of electric field or voltage, you have a band bending. Okay, so the band bends, and naturally, if you have a slope here, because this is like a top of the mountain, and then you have electrons which they can just roll down because the potential energy is lower on the other side. Okay, so due to this change in potential energy, so it is like they are rolling down the hill, and that is how you explain the flow of charge carrier or electrons. So this is another important concept which schematically actually is used when we talk about semiconductor devices, that whenever we have an energy band, like a shown here on the left side, so it will bend when we are applying an electric field. Okay. So, two things which I think you need to remember here. Uh, so when we say electron, what are the properties of electron in the band? So what happens? So electrons, there will be a change in momentum due to this applied electric field, and that will lead to a bending of the band, and the second thing is electrons, only electrons which are really close to the Fermi level, so they only contribute to the conductivity. So all other electrons way below the Fermi level, they really don't contribute to the conductivity. Now, and another thing which you should also remember, that whenever we talk about this conductivity, so electrons need available or unoccupied state, so that you can achieve a conductivity in the of electrons. Okay, so so here we are always looking at the band structure or the picture of the energy band, and then we want to explain or understand the conductivity of the electron. So in that sense, if we talk about flow of electron, so we need to have unoccupied levels. So then only we can say there is a conductivity of electron. And how do one can move these electrons? So there are many ways you can move this electron. So how do we move electrons? So here, so one example, so in a band, so how do we move electrons in a band? So one here we saw is by applying an electric field. So if you apply electric field, you can bend the band, and you can then create like a hill-like structure or hill where the electron will flow downhill, basically by applying electric field. Any other way you can do that? Anyone? How we can move the electron in a crystal or in a solid, or basically in a band, how we can move electron uh, uh, from one energy state to another energy state. Yes, so if you, it's like a thermal, so if you increase the temperature, the thermal uh, activation, let's say, so which will, you can provide heat or temperature, and then you can also move the electron. Any other way? So another is using photons, like if you shine light or illuminate it, then you can also provide a energy HF, or whatever you call H nu. So you can provide energy, so which will basically, these electrons will absorb that, and then they can move within the band from occupied to unoccupied state. Then any other way? So these are the only three fundamental ways we can move electrons. Anything? So another is you can also apply pressure. So by applying pressure also, you can also modify the band, and then you can move the electron from occupied to unoccupied level as well. Okay. Okay, so this is about this. So these fundamental things which I described, so they are applicable to all kind of materials actually, and only the picture might differ a little bit when we go from metal to semiconductor and so on. So far what I have described is about metals. So now let's look at the semiconductor. So we take the example of silicon. Okay. So silicon has an electronic configuration 1s2, 2s2, 2p6, 3s2, 3p2. And now we want to know how we can have band in a semiconductor. Particularly, we take this example of silicon and how this formation of band takes place in silicon. So here in the picture again, what is shown here, so you have, so this is the electronic configuration. One is what I described just right now, and the 3p and 3s level are the highest occupied energy states. And when we look at the 1s and 2s, 1s, 2s, and 2p, so they are all fully filled cells. Okay, so the orbitals are fully filled. That means, and they are also really core, very close to the nucleus. Okay, and that's why their overlap will be minimum, or there will be no overlap of these orbitals when two silicon atoms interact. So now if you bring, so this is one silicon atom. Now if you bring a silicon and silicon atom, so this 1s, 2s, and 2p, so they are the core orbitals, and they do not overlap. And that means they will not really participate in the formation of this energy bands, and they will definitely, they are not participating in the bond formation, and they will also not participate, or we can neglect them when we consider the band formation in silicon. Okay, so only this 3s and 3p orbitals will form or will overlap. Okay, so they will overlap and form the bands. Now, if you look at this silicon solid or silicon crystal, you know, so each silicon atom bonds with 4 silicon atoms, right? So why 4? Because although you have this, you have 3s and 3p. Okay, so you have 3s2, which is already fully occupied or fully filled, but still, and you have 3p electrons. So one is empty. So why then you have 4 electrons or 4 silicons? They form a bond. This is due to something known as hybridization. I think you know already about this. Let me know if you don't know. So hybridization happens. So you know, I think in carbon, this hybridization takes place. So what is this hybridization? This is the sp3 hybridization takes place, and due to this sp3 hybridization, so you have a formation of 4 sp3 atomic hybridized orbital. So you have sp3 hybridized atomic orbitals with 1 electron each. So in a way, so we can say you have 4, let's say you have 3s, 3px, 3py, 3pz, and then after hybridization, what happens? So you will have sp3, so 3 or 4 sp3 hybridized orbital, so which have what is, why do they form? They will be the energy will of these hybridized orbitals will be lower than the total energy of this 3s and 3p orbitals basically. So if you have here 2 electrons, or like 2 electrons here and one here, so in the hybridized orbital you will have these 4 hybridized atomic orbitals, each will have 1 electron each. Okay, and they form a degenerate hybridized orbital state. That means they have the same energy. All these hybridized atomic orbitals will have same energy, and that's why you will have a silicon bond with like 4 atoms, very similar to your carbon as well, right? And so each hybridized orbital, again, this atomic orbital can be represented by a hybridized wave function, hybridized atomic wave function. So you can say hybridized, name here. So each orbital will have a corresponding wave function, psi hybridized orbital sp3, and now they will overlap. This sp3 hybridized orbitals will overlap and form the silicon-silicon bond. So this is what again shown here in the picture. So you have an isolated atom. So you have 3s, 3px, 3py, and 3pz with certain angular distribution, the probability distribution. But when this silicon goes to form a bond, so you will have this hybridization will take place, and then you have this formation of a hybridized sp3 hybridized orbitals, and the bond angle, so they will form like 109.5 degrees, this bond angle, which will be your tetrahedral symmetry. So they will form. They will form a or arrange this sp3 hybridized orbital in a tetrahedral symmetry, and each orbital will have one electron. And now, since each orbital is half filled, so they will now they can make a bond with another silicon atom or another atom which has another unoccupied uh, or half-filled orbital. So, and then they will form a bond. So, example will be, so silicon is of course the silicon bond will happen due to this hybridization. So you also have formation of SiH4. So the 1s orbital of hydrogen, they can also form a bond with silicon. So this is a very famous uh, gas, let's say silane, which is quite used in silicon semiconductor industry. So to make silicons actually. So very similar to like your methane, CH4. Okay. Where carbon, you have hybridized carbon sp3 orbitals, which form four, or they make a covalent bond with this fourth hydrogen atom. Now, the question is, how do they form the band? So, okay, so now it's time. So we will then continue with it tomorrow. Okay. Any question? Pattern of quiz. I said no online, so mostly multiple choice. We do multiple choice. Okay, anything else? No? Okay, then thank you. And we'll see tomorrow.